So in this video we will talk a little bit about the Kirchhoff's first law. So the Kirchhoff's first law is also called basically the Kirchhoff's basically current law, and they also call it KCL. They call it KCL, right? So what that means is that, so first of all, Kirchhoff was a physicist, and it seems that he was an experimental physicist in the 1800s. His name was Gustav Robert Kirchhoff. He was a German physicist who contributed to the fundamental understanding of electrical circuits, spectroscopy, which I don't know what that is, and the emission of blackbody radiation by heated objects. And he coined the term blackbody radiation in 1862. So he was born in March 12, 1824 in Königsberg in Germany. Of course, I suppose must have been in Germany, and died in October 17, 1887 in Berlin. And his name was Gustav Robert Kirchhoff. And he seems to have also discovered two elements as well, which is of course interesting. Anyway, so what he has done is that he has, as far as I know, he has basically two laws, basically. The Kirchhoff's first law and the Kirchhoff's second law, at least when it comes to basic electricity and electronics. So you have he has the first law and the second law. The second law is called the Kirchhoff's voltage law. And the Kirchhoff's voltage law is about voltage in electric circuits. In a particular way, voltages add up to the supply voltage. And the Kirchhoff's current law is about basically the fact that the currents coming into basically one node in a circuit, and the currents going out, the algebraic sum of those currents is equal to 0. So it's basically what these two laws are. So what this KCL means is that, suppose that you have, for example, a simple circuit like this. So you have basically, suppose that you have these two resistors, and they are connected in parallel to another resistor, and the whole thing is connected to a power supply, for example. The whole thing is connected to a power supply. Now this power supply is positive, negative, and that is your power supply. And basically what this is that, let's say that, for example, this is the current going through your circuit I, and then you have I1, the current going through this branch I1, and there will be, of course, another current going through this branch, which we can call I2. Now the Kirchhoff's current law says that relative to any point or any node in a circuit, if I call this a node, there is some current that is coming in, right? At any node, some current is coming in, some current is going out, and of course the currents coming in and going out must, the quantity of those currents must be the same, and they must cancel each other out, otherwise, at least logically, it makes no sense. So about this, for example, particular node, if I call it, for example, Z, this I is coming in, this current I is coming in, then I1 is going out, and also I2 is going out this way. And what Kirchhoff says is that basically if I think of the currents coming in as positive currents and the currents going out as negative currents, then you have positive I, and if I add all of them together, having in mind that currents coming in are positive, currents going out are negative, so then you would have positive I, negative I1, because it's going out, it's negative, negative I2, again, it's negative, it's because it's going out. The sum of them, the algebraic sum of them, or I can write it this way as plus I, plus negative I1, plus negative I2, the sum of all of the algebraic sum of all of those currents is equal to 0, right? And you must know from your basic electricity or basic electronics that this is just simply a parallel circuit, meaning that I can think of this circuit as basically, if I think of these two resistors as just one equivalent resistance, and then you have another resistor here, and then if I connect both of them to a power supply, I will have this circuit here. Now this is a parallel circuit, and in a parallel circuit we know that basically, even if you don't know anything about Kirchhoff's current law, you know that in a parallel circuit, if you have a lamp, for example, that draws 1 amp current from the power supply, if you connect one of those lamps to your power supply, the lamp will start glowing, and so 1 amp is going through your circuit. I is equal to 1 amp. Now what happens is that if you want to connect a second lamp, so of course you would normally connect the second lamp in parallel with the first lamp, which would be this thing over here. And again, this lamp, assuming that it's the same type of lamp, it draws the same type of current. So if 1 amp is call it I1, for example, is 1 amp going through this branch, this lamp does need also 1 amp of current, which means that I2 is equal to basically 1 amp. And so the 1 amp will be added to the total current of your circuit. And so if you add the third lamp, then you would need another 1 amp of current, and the 1 amp of current would be added to this, and so on and so forth. Meaning that the individual currents of each of the branches in a parallel circuit will add up to become the total current in the circuit, right? Which means that I can in the case of this particular case, I can say that if this is I2, and if this is I1, and if this is I, the total current, I can say that I is equal to I1 plus I2. That we can say, and that always holds. And you can basically rearrange this equation as well, meaning that you can write I is equal to, take this to the other side, this becomes positive I1. Take this to the other side, this becomes positive I2. And then I is equal to I1 plus I2, so you have the same thing basically, meaning that it's the same thing as the Kirchhoff's current law. And so that's basically what Kirchhoff's current law basically is. And for every point you can do the same thing, or for every node you can do the same thing. This node, for example, I2 is coming in, I2 is going out. I2 coming in, if I take it as positive, and I2 going out, take it as negative, that is supposed to be equal to 0, which mathematically also makes sense, which means that I2 is equal to I2, which is of course true, right? So that's the Kirchhoff's first law, or KCL. Okay. Now let's do a couple of examples here to understand the Kirchhoff's law in the context of an example. So I guess we are going to need some. So if you have, suppose that you have, for example, the same circuit. Suppose that you have the same circuit that we had before, and you have one resistor here, and then all of these are connected to a power supply. Now, suppose that all the three resistors have values of 100 ohm, meaning that, for example, if I call this R1, R2, and R3, suppose that R1 is equal to R2 is equal to R3 is equal to 100 ohms. And suppose that I1 is 2 amp and I2 is 1 amp. I1 is 2 amp, so this is I1. This is I1 and this is I2. Suppose that I1 is 2 amp is equal to 2.0 amp and I2 is equal to 1.0 amp. And based on what we talked about in the previous video, you must know now the number of significant figures here, and so you now understand these numbers pretty well. So now what we want to do is that we want to calculate the V of S, or the power supply voltage in this circuit. So I know that basically 2 amps is going through this branch, 1 amp is going through this branch. I know that each of these resistors is 100 ohm, 100 ohm, 100 ohm, and I want to know what is the supply voltage here. So you can apply the in order, of course, to calculate the voltage. You know that V is equal to I times R, Ohm's law. So I can, of course, calculate the equivalent resistance in this circuit, meaning that you have 2 series resistors here, 1 parallel. You can calculate that, there's no problem with that. But I need the current, the total current going through this circuit, which is I. That I don't have it yet. And then when I have I, then I can also calculate R, put the 2 in this equation, and calculate the power supply voltage. So what I'm going to do is that first I'm going to calculate I, for example. So for example, you can think of the Kirchhoff's first law, or KCL, for this node here. So you can see that I is coming in, so positive I, and I1 is going out, and I2 is also going out. So these two currents are going out. So negative I1, negative I2 is equal to 0, which means that I is equal to I1 plus I2. So now I is equal to, basically I1 is basically 2 amp, 2.0 amps, plus I2, which is equal to 1.0 amps, which is the same thing as 3.0 amps. I is equal to 3.0 amps. So the total current going through your circuit is 3.0 amps. And now if I calculate the equivalent resistance here, we will be able to calculate voltage. Okay, so basically now we know that 3 amps of current is going through the circuit, And to calculate the equivalent resistance, you have basically R2 and R3 are in series, so you have 100 plus 100, which is basically 200 ohms, right? So R2 plus R3 is equal to 200 ohms, and R1 is in parallel with this resistor, which means that you have 1 over R is equal to 1 over R1 plus 1 over R2. This is how you calculate parallel resistors. This is the equivalent resistance or total resistance. So you have 1 over R of T is equal to R1 times R2 and R1 plus R2, which means that R of T is equal to R1 R2 over R1 plus R2. Now one of the resistors is this resistor here, and the other one is another 100 ohm resistor. That means that R of T is equal to basically 200 times 100, and the other resistor is basically so you have 200 plus 100 over here, which is the same thing as basically 20,000 divided by 300. This is your R of T, and that's the same thing as basically 200 thirds. 200 thirds ohm, basically. So your R of T is equal to 200 thirds ohms, and therefore the voltage that's going through your circuit is V is equal to IR, and therefore V is equal to I, which is 3.0 amps times 200 thirds ohm, 200 thirds ohm, which is the same thing as 3 and 3 you can cancel out. You have 200 volts, basically 200 volts. So that's basically one way that you would use the Kirchhoff's first law, or KCL. Another example that we have is basically you have, suppose that you have a resistor here and another resistor here, and you have another resistor here, and you have another resistor here, and you have another resistor here, and basically over here some current is going in, some current is going in, and over here some current is going out, and going out. And this is a point, you can call it, for example, Z, for example. And you can call this, for example, I1, for example, I2, I3, I4, and I5. Now, let's suppose that, for example, basically we have two resistors here. Let's call these, for example, R1 and R2. So R1 is equal to R2 is equal to 100 ohms, and all the three resistors are 10.0 ohms. So R3, so you have R3, R4, R5. R3 is equal to R4 is equal to R5 is equal to 10.0 ohms. And the current through each 100 ohm resistor is 500 milliamps. each 100 ohm resistor. That means that through R1 and R2, these two currents are 500 milliamps. So I1 is equal to I2 is equal to 500 milliamps. And the question that you want to answer is, what is the current through any of the 10 ohm resistors, these three resistors, assuming that the current is equally distributed among these three resistors. So that means that basically each of these currents I3, I4, and I5 is 1/3 of the current exiting this node basically. Now, if we write basically the current going in, or basically if you write a KCL equation for this node, we can say that, for example, I1 and I2 going in, so I1 plus I2, and this is also positive, and these three are going out, so minus I3 minus I4 minus I5 is supposed to be equal to 0. The algebraic sum of all of these currents is supposed to be equal to 0. Now all of these currents are going out, right? So I write this as I1 plus I2 and take a negative sign out here. So you have I3 plus I4 plus I5 is equal to 0. And since we know that basically, since we know that each of these currents is 1/3 of the total current exiting this node, the total current exiting this node is of course the sum of all of these three currents, meaning that I can write basically I3 plus I4 plus I5 is basically the total current exiting the node. I call it, for example, I of x, for example, right? So I can write this equation as I1 plus I2 minus I of x is equal to 0. And therefore I1 plus I2 is equal to I of x, right? So now this way we can calculate first I of x, the total current exiting the node, and then we will be able to calculate each of these currents based on based on the fact that basically I3 is equal to 1/3 I of x, and I4 is equal to 1/3 I of x, and I5 is equal to 1/3 I of x, because the current is equally distributed among the three resistors. So I can write these equations. So now basically what I can do here is that I have 500 milliamps and 500 milliamps for I1 and I2. Now 500 milliamps is the same thing as here basically when you add 500 and 500 you will get 1000, right? So sometimes in order not to lose the number of significant figures that you have, you need to basically write your numbers in scientific notation, meaning that, for example, here, of course, if I write, for example, 500 milliamp plus 500 milliamp is equal to equal to I of x, and so 1000 milliamp is equal to I of x, and so what that means is that the current exiting the node is 1000 milliamp, and so you can say that I of x is equal to 1 amp, and therefore basically then I of 3 is equal to I of 3 is equal to 1/3 of this, so 1/3 amps, and I of 4 is equal to 1/3 amps, and I of 5 is equal to 1/3 amps, right? So these are basically the of course, technically, for example, you would write this as 1.00 amps because you have 3 significant figures here, and when you add these numbers together, you'll get 3 significant figures, meaning that you could write this as actually you could write this as 1000 milliamp, and then when you want to write this as in amps, you could write this as, for example, you could write this as I of x is equal to 1.00 amp, for example, and then basically I of 3 would be equal to 1.00 divided by 3 amps. Then I of 4 would be equal to 1.00 divided by 3 amps, and I of 5 would be equal to 1.00 divided by 3 amps. And the reason why you should do that is that if you say 1 divided 1/3 amps, then this number would have only one significant figure, and if you divide it by 3, of course, you would get 1/3 is the same thing as 0.333 repeating, right? So that would be 0.33 repeating. Now, depending on the number of significant figures that you have here, then you would write that number either as 0.3 if you have one significant figure. If you write 1.0 divided by 3, that would be 0.33. If you write it as 1.00 divided by 3, that would be 0.333, because you have 3 significant figures. So you can write it that way, or that's basically how you write it. Now this business of significant figures is a little bit tricky, and you need to keep track of that in your work, and depending on the situation you have to do different things. But essentially, once you've done enough examples, you should be good to go. So you don't need to worry about the fact that you cannot do it from the get-go. It usually takes some time to get familiar with how to deal with these numbers. It's not a simple thing, and it essentially takes some time. But once you spend a little bit of time in physics and doing some problems in physics, in electronics, then you're good to go. Now the next part of this question is, what is the voltage then across any of the 10 ohm resistors? So the 10 ohm resistors, over here we have R3, R4 and R5. These are 10 ohm resistors. You want to calculate the voltage across them. So you know the resistance, you know the current through them. So you can just simply write V is equal to IR. So V is equal to I, which is basically 1.00 divided by 3 amps, times R, which is the same thing as 10.0 ohm. 10.0 ohm. And of course I don't want to write ohm over here. So you can see that this number has 3 significant figures. This number has 3 significant figures. When you get your final value, you should have 3 significant figures, and that is basically 10 times 1 is equal to 10 thirds is equal to 33.333 and so on and so forth, right? 10 thirds would be, sorry, 10 thirds would be 3.333, because 1/3 is 0.33, so 10 thirds would be 10 times that. So so you would have 3 significant figures. That means that, for example, V of R3, for example, would be, for example, 3.33 volt, for example. Or you can say basically, or you can also call it, for example, 10.0 thirds volts, for example. We can write it that way as well. And there is other considerations as well regarding these significant figures, but then we will have to come across proper and appropriate situations so that we can talk about them. Otherwise, there is no point in talking about everything unnecessarily. And then, of course, V of R4 and R5 would be the same, because the amount of resistance is the same and the amount of current going through them is the same, so the voltage drop across them would be the same. So that means that V of R4 is equal to 3.33 volts, and V of R5 is also equal to 3.33 volts, right? So that is basically Kirchhoff's first law, or KCL. Now in the next video we will talk a little bit about Kirchhoff's second law, and then we have a couple of other things to discuss here. So I'll see you in the next video, and thank you.